Yes.
Can you see it?
Yeah, we are seeing it.
Okay, perfect.
Thank you a lot.
Okay, so once again, I introduce myself. My name is Sergey Lesnik. I work at Wikki, and together with Henrik Rusche, we took care about the grain challenge of the exaFOAM project, one of the grain challenges, the Combustor one, and also participated in several developments. One of them was the dynamic load balancing. Another one, which I will mention as well, was the coherent file format. Yeah, and that's also our key mission at Wikki, to introduce developments and better to say, to develop algorithms that can help customers to to accelerate.
Sergey,
Yes.
just one thing. I don't think that you're using the microphone. Maybe you're using the audio from your laptop. The audio is
Oh,
not so clear.
Flavio, is it better now?
Oh, it's much better. Thank you, Sergey.
Sorry for that. It's yeah. Okay. So let's move on. Let's talk about an exaFOAM project. I have here an overview over all work packages, and I will guide you through this exaFOAM setup of work packages while I introduce the results of the Grand Challenge. So first of all, in the work package 2, we are dealing with the benchmarks, where we have industrial benchmarks, also micro benchmarks. We set them up, publish them, and then test the improvements of which deliver the developments of the exaFOAM project. And one of these cases was the Combustor Grand Challenge. So let's have a look at this. It's based on the experimental setup, confined jet high pressure from Severin, from the German Aerospace Center. It's about a high fidelity numerical simulation, so an LES of a generic gas turbine. And the goal is to identify thermoacoustic excitation, which may damage the gas turbine, and also to analyze the pollution formation mechanisms. So short to the geometry, we have a main inlet where the premixed fuel mixture enters. We also have pilots here where also the fuel mixture enters with a different mixture on itself, and we have here a combustion chamber. So the case was about, the largest case is about 500 million cells. It has it was run on 33,000 cores, and we estimate for a production run you would need somewhat about 4 million core hours. And we used exaFOAM solver for testing. I have a video here. You see it's an actual simulation result, in casing. And if you remove the casing, then you can see the combustion itself. Here we have the pilots, the main inlet pipe. In the center is the fuel mixture, and the flames. These are actually the temperature controls around this fuel mixture. So we set up this case, we run initial tests on our systems, and then through the work package 7, we publish these cases, so they are available for public as well. And I have small screenshots of the two sites. So one website was presented by Flavio, right, with the benchmarks overview, and on the HPC committee page, we also have for every benchmark a README file, so you can learn about every benchmark specifically. Then after this, we wanted to run the case on the larger machines, so we applied via work package 1 to HPC resources, and we got an access to Hawk cluster from HLRS. Has been already introduced here. We have an AMD architecture Zen 2 with 2 by 64 cores per node, pretty large L3 cache. Yeah, and we run the largest mesh on this machine. On the right hand side, you can see a strong scaling diagram. So for strong scaling, we have on the x-axis the number of cores, and on the y-axis I have a speed up here. So if we have twice as number of cores as the base case, then the ideal speed up would be 2, and for 4 it would be 4, and so on. And what we can see here is the similar picture as Charlie have shown before. We have a super linear speed up, right? So we get twice as much resources, but the speed up is higher than 2. And it continues up until 8,000 cores, but then it breaks. We just took it as a result, but then the colleagues from the Barcelona Supercomputing Center did a profiling on this and found a problem. So in the turbulence model, we have a problem that the cell wall distances were computed every time step. You wouldn't need it to do it every time step. So we talked to the ESI and talked about this problem, and they implemented a solution in the work package 3 code restructure, right? And then, oh, it's sorry, for some reason got quite small. I show it not in the presentation mode. And then, as you can see, the result before is the green line, and the line with the algorithmic improvement implemented by ESI is the orange one, and the best performing case got just 10 times faster. Yeah. You might ask yourself, we have still super linear scaling here. Why didn't we test the next point, the one with somewhat 65,000 cores? And the reason for this is the I/O. So we have a problem with I/O. We just couldn't decompose the case for such high number of cores. Go again to presentation mode. So that's another task of the work package 3, the current file format, which will be presented by Gregor Weiss. And we also worked with ESI to integrate this into the OpenFOAM. And here you can see the latest results. These are fresh results, just I think we got it one week ago. And what you see here on the right hand side is again, it's not a run, but it's a decomposition itself as pre-processing step. run with collated and with the coherent. And as you can see, the coherent file format allows us to decompose the case under 20 minutes, independent of how many partitions we want to have. And it's for the largest decomposition, it's 60 times faster, and we also are able to decompose even for larger decompositions. Okay, so once we done this, we did this algorithmic improvement, and the code was back to the profiling work package 5, and they did more analysis with the profiling tool extry. So what you get from extry, you can see here. What you see is one pimple iteration, and the colored regions are the linear solver executions, and yeah, the gray regions here in between is rest of the code. So we just wanted to look at the linear solvers. And here you can see that we have some peaks, right? For some, oh, sorry, I need to mention that on the y-axis we have MPI ranks. X-axis is the time, execution time. And for some MPI ranks, we have strange peaks here, which somewhat indicate an imbalance. If you look closer here, yeah, you can see it maybe better. Then we went to the code and tried to analyze what is happening there. So the hypothesis was that the time lag between the MPI ranks is due to imbalance in the number of boundaries, because we saw it in the decomposition log that exactly for these ranks it's another number. It's quite a big difference to the other ranks. And we found exactly 11 occurrences of FVC schemes in this code, right? So we just looked for FVC word in the code, and we asked the profiling team to look for MPI weight-alls, and found exactly 11 occurrences of this. Okay, and as you can see here in this MPI diagram on the bottom, there is a lot of time spent in MPI weight-all and also MPI all reduce. You can see here, which is wasted time, right? So if you could balance the work and could gain this time into the computation, that would be great. And this is about what Henrik Rusche will talk about. And this work package, this task was in work package 4 and dealt with load balancing. So Henrik, the stage is yours.
Can you hear me now?
Yes.
Yes.
Okay. Okay. So I will give you some information about the work package 4, the work that we did on load balancing. And load balancing, what we describe of that is the idea of shifting work from one processor to another. And we have all of that machinery in various versions of FOAM, actually in FOAM Extend, but also in of 11. And the way it works there is that you shift cells from one processor to another using topological changes. And that's depicted on the right-hand side. So you have processor 1 and processor 0, and they exchange the cells. And because it's a topological change, this is quite expensive. There is also an issue with the metric that you want to use for load balancing. So if you think decomposed power, then the metric that we use there is to level the number of cells. That is our primary goal and objective in the load balancing, in the decomposition. However, as Sergey already mentioned, this is not the only metric that should be used. The number of processor boundaries and also distribution over the machine is important. You could also say that the number of phases is important because those are the big loops in the sparse matrix multiplication, and so on and so on. And I can name a few more. And so it's hard to guess estimate the load a priori, because you need that to do the shifting. And it also may vary in different sections of the code. And to make this more complicated, there is also load imbalance that comes from interrupts and network latency. So it's stochastic. So there is nothing you can do a priori about it. And so what we thought is that we need something that is complementary to that large-scale load balancing. And we call that fine-grained load balancing. The next page, please. Okay, and spawned off with some information from our colleagues from BSC, Barcelona Supercomputer Center. We looked into a Levy approach, which is lend when idle. And the idea there is that MPI ranks lend their resources as soon as they enter a synchronization point to a rank that has not reached that synchronization point. Okay, and you will say, okay, but well, they are not sharing the memory. And so we use a trick there, but that is the idea. So you use resources on the same core, on the same CPU, and you make some communication between the MPI ranks. So contrary to what I described before, the classical load balancing, there is no data. No data is being moved. So this is much more agile and can be used to level on a much lower granularity. Apparently, well, not apparently, this has been packaged by BSC into the DLB library, and we had some issues. So we re-implemented DLB natively into OpenFOAM using a bunch of threads, atomics, and global shared memory to communicate between the MPI ranks. Next slide, please. Okay, so one of the questions that arise now is how do you get some parallelism into the into OpenFOAM, which isn't there. Yeah, every MPI rank runs in a serial manner, and even if I wanted to do split the work, I need to parallelize it in some way. Note that all of the ranks, all of the CPUs are populated. Yeah, so I don't want massive amounts of parallelism like for OpenMP. It's enough if I can split up, let's say, do some parallelism per rank for 2 threads. And what I came up with here is that we can do, this is easy for the big loops. So for a cell loop, you just split it because that is easily parallelizable. But for the more complicated one, and I take SPMV as an example here, what I do is I divide the cells into regions of cells. And then I can make interdependency and store that in bitmaps, which allows me to do the dependency calculation very quickly and dynamically. Okay, so that's where the parallelism is coming from. Next page, please. Okay, so what are we trying to do schematically? And I picked the sparse matrix vector multiplication plus the dot product, because after the dot product, there is usually an MPI reduce, because you want to do have a global residual, for example. Okay, so the MPI reduce, which you see in the graph on the left, it's on the right side. Yeah, so there is the MPI reduce. Everybody has to agree on a number and communicate it back. So that is a synchronization point. And at that point, you would like everybody to be at the same, would reach that point at the same time. So, so what is depicted here is simplified graphical representation. There is two processors, one is A and one is B, so all the processors are denoted by capital letters. There's also a C, D, E, but they are not, they will have also those timelines. Yeah, time is going from left to right. And but they are not depicted, I just wanted to show what is happening between two processors. Yeah, so but you can have 8, 10, 1024, whatever. The blocks in green, that is computational, that's boundary communication. So you would like to send something. The yellow stuff is computational work. In this case, is the SPMV. There is some idle time. There is some computational work with the dot product right at the end before the MPI reduce. So first thing I tried to parallelize the dot, yeah, because that is easy, trivially to parallelize. And it turns out, well, that is so small, there is no point. There is just nothing to share, because the operation is so small. There is nothing to do. Yeah, because the swapping, shifting the work, it all costs, and there is just simply no time. So the next step further is to go into the SPMV, and there is this MPI barrier on your way, which is sort of relaxed in the later ESI versions, but when we started, it was still there. And this is just a picture of what is happening, and you can spin it out to other operations. So to remove that MPI barrier, you have to make some changes to pstream, and also you do the polling in a different manner. So and one step more, when you go from the left, which is the baseline, to the improved version, is that you chunk the work in the SPMV, the A on the A processor, into 2 blocks, and you shift one of the blocks from the slower processor B into A. So technically, this is not done by moving the work into the MPI rank, but by spawning another thread and starting the thread in parallel on rank B, using the CPU of B to accelerate the work in A. Okay, so next slide, please. What Sergey showed is that for the DLR Combustor, it is very important that you look into the calculus operators, not so much in the solvers, because the DLR Combustor, as well, and this is also true for the other high fidelity cases like the NACA CRM. This is just as much matrix assembly and as solution. So the split is maybe 40% in the solver, 60% in matrix assembly, gradient calculation, and everything else. Okay, so we need to look, if we want to make progress, we have to look into both. And the normal narrative is that, okay, you have to improve the solvers, but for the high fidelity, that is not actually the case. So the similar situation can be done for the gradient, and there the situation with the communication is different. In OpenFOAM, the pairwise communication is not hidden under the core operation, which is a problem. So you have lots of weights. But that can be avoided in the similar manner that I showed for the SPMV. Keep going. Next slide. Okay, so here is a busy graph. So what I have here is a trace with score P. So it is, so what you see here is the reality rather than the graphical representation that I showed before. Yeah, so each block that you see with the colors is a operation. Time ticks from left to right. For the baseline, we have 8 ranks, MPI ranks. And the red ones, the red sections are something where MPI is waiting. So if you look right to the right end, there is a lot of MPI reduces. So that's where everybody wants to synchronize. And in between, you have also MPI weights that are scattered. So that's when a processor waits for a message to arrive. And what you see here is a bit out of the DLR Combustor. And there is a little bit of gradient calculation and interpolation and a little bit of SPMV, I think, in the end, last 10%. Okay. And with load balancing, the picture has changed. That is on the bottom. That's with load balancing. So one thing you notice is that suddenly I have 16 threads. So I have 8 ranks, but on every rank I have two threads running. I have the master thread that was started with MPI, and then I spawn another thread. And I use that to schedule extra work that I generated with the chunking. And so things you notice is that, for example, if you look at the right-hand side, the MPI wait time is quite reduced. It was pretty big on the left-hand side. It's hard to compare those plots because they are different realizations. Yeah, so depending on how the machine runs, they're never the same. But you can still draw a lot of information, pull a lot of information out of these plots. So what you notice is that a lot of the red has disappeared, and the operations seem to be a little bit more synchronized. Okay, keep going. So this is a close-up, making the same points. Keep going. Okay, one important point that I want to make here is that what the system that we have in place now allows you is to do several operations at the same time. And I picked this section out of the trace. And what is happening here is that we do a gradient, an interpolation, a Laplacian, and various field operations at the same time. And if you have everything synchronized, well, that is not quite possible. Yeah. So the pairwise communication, they can drift, as Sergey has shown, but there is a limit. At some point, you need that result, yeah, and you wait for it. So, but here I can overlap all of those operations. Okay, next slide. Status. Okay, so what we have here is a version where we can do load balancing with one additional thread per rank. The scheduler is generic, and it sees the operations as wrapped classes. The scheduler is NUMA aware, so it will assign the closest CPU to some work by looking in Harvey log and finding out, because that knows all of the cache hierarchies on your CPU. So it uses all of that, leverages all of them. What you saw there, we currently implemented the method for SPMV, for the gradients, Laplacians, and also pieces of the thermo library that turned up to be a big problem. Calculation of CP takes different time on different processors, and largely because the boundaries have a different size. So that is another piece of metric that nobody considers. Execution of operations may overlap. The approach is incremental. So with this, we can go through the code and do one operation after another. So it's not we have to do it all, everything, and nothing works. So it is incremental. Yeah, we can do pieces of thermo and we can do pieces of algebra, one at a time. And we do extensive analysis using SCORE-P to find performance bottlenecks. As you will see, it still exists. Okay, keep going. So we tested this approach on our rotating wheel. This is where I started. So it also helps you with the AMIs because their communication is an issue. And that was 10% faster. We did the Russian turbine with Andreas Ruop at HLRS, and the speed up was 5%. You have to keep in mind that we expected that the benefit you would only see when you go to larger core counts. Yeah, so there isn't that much idle time on a single node execution. There is something, but it is not a factor of 2 or something like that. Yeah. So we went to the DLR Combustor with a 3 million cell case, which is representative for the large ones, but on a much smaller core count. And the results as they stand are a little bit disappointing. Yeah. So on small core counts, we get something like break even. So DLB and baseline are about the same. But when we go to 2 nodes, we get 14% penalty. And I expect that to get a little bit better. And I hope to get, because there is still things that we see in the traces that should not be there. So we are trying to improve, but as it stands at the moment, we have no benefit to report. Keep going. At least on a DLR Combustor. Okay, so conclusions. It is possible to remove idle time from MPI barriers, as we've seen in the traces, and lending compute resources from one MPI rank to another. Okay, we generate that parallelism by chunking the matrix and other operations. And so the approach yielded mixed results. So for some cases, it is faster, but where we really wanted it to deliver, as on the DLR Combustor, at the moment, we don't see that. And one of the things could be that the cell count, as you've seen, it becomes smaller and smaller. So we are at the 256 cores for a 3 million cell case. We are already at 11,000 cells. If you shrunk that by 32, you can count. Yeah, there isn't a lot of flops that we are trying to shift. So now things that you pay, like context switches between the processes, kill you. And I think that is my conclusion. But even tracing on 256 cores is a challenge, but we are working on that. So to find out what is actually happening. I think we want to keep that still in mind, because this low-level load balancing might be good, because if we have more difficult metrics that we cannot work a priori, or go for extend open form to something that is MPI and threading, or have hybrid matrices, asynchronous solvers, all of this will come back to us. So I think it is a good technology when it is combined with others. Okay, so much from me. Thank you very much. Thank you again to our colleagues from HLRS and BSc that have been involved in large parts of this work.
Thank you a lot.